Right, we had a question about this problem. Here we have two bars. We have a core bar with a constant cross-sectional area A1, and we have a sleeve with a variable cross-sectional area A2 equals A1 over 1 plus x over L. So we can see that as x increases from 0 to the length of the bar L, we can see that A2 is decreasing. So in this problem, we heat the setup, and we want to know what is the total elongation of the bar under heating. So there are two parts to the problem. In the first one, the core and the sleeve are bonded to each other along the entire length of the bar. But in the second one, they're not. There's a space between them, but they are secured to a wall at the end which we can move. So it's free to move. So as we heat it up, it's going to move to some new position. And in both cases, the total length of the core and the sleeve is the same throughout. And so the question we had was, what's the difference between them? How do I solve these two problems? They look the same. I can see that the setup is different, but I don't know how to consider them. Well, we have our constitutive relations for the link between our temperature change and our change in strain. But really, the fundamental difference between them is how we consider the strain in each. In this first one, because it's bonded throughout the entire length, we know that for all cases, the strain in bar 1, the internal, the core, as a function of x, is equal to the strain in 2 as a function of x throughout the entire length of the bar. But in the second one, we know that because of the change in the cross-sectional area, whereas the strain is going to be the same throughout this bar, at every point in this bar it will be a constant. Here, because of the change in area, there's going to be a difference in the stress that bar will have inside as a function of x. And so we can see that the strain is likewise going to be different as a function of x. So we cannot say that the strains are the same throughout. We can't say that. But what we do know is that because they're secured to the same wall at the end, we can say that the total elongation of that bar, the total elongation, not as a function of x, simply a number, is equal to the total elongation of bar 2. And what do we know about elongation? We know that elongation is equal to the integral of the strain as a function of x. So we can rewrite this as the elongation, the strain in bar 1 is equal to the strain in bar 2 when we integrate along the entire length of the bar from 0 to L. The strain in bar 1 integrated from 0 to L is equal to the strain in bar 2 integrated from 0 to L. And so you can write down your constitutive relation for the strains, and then you can go ahead and integrate, and you'll find that they will end up being different. Very good.